I'm Brian Storey. I'm Director of Gateway Antarctica, which is the Centre for Antarctic Studies and Research here at the University of Canterbury. I'm a geologist. I'm going to talk on what if Antarctica warms tonight. I did my first degree in Trinity College in Dublin. Then 1974, I got a job with the British Antarctic Survey, and that got me involved in Antarctic research. And I stayed pretty much with the British Antarctic Survey till the year 2000, doing Antarctic geology research. And then I came to New Zealand in the year 2000 to be director of the research centre here at the University of Canterbury. And I've been in that job till today, at least, and hopefully into the future. But we'll see what happens. Okay, so that's the question. And really, you know, there's a very simple answer to this question. And this is it. The ice is going to melt. That's one thing for sure. You notice I stopped it just sort of below John Key's office window. And he probably wouldn't notice because he doesn't seem to be noticing much about climate change and what's happening. Actually, if all the ice melts in Antarctica, it's going to rise to the top of the flagpole, approximately 70 meters. So it'll cover all the offices in the beehive. So that's the sort of quick answer. Maybe we can all go home now. This is what Antarctica would look like if the ice completely disappeared. Lots of mountains, lots of rocks for a geologist like me to look at. But I just want you to notice the large areas of West Antarctica in particular on the left, and some of East Antarctica that are below sea level. So that's quite important that we'll come to a little bit later on. What would Canterbury look like? Well, this is what Canterbury would look like if we were to melt all the ice on Antarctica. As I say, there's 70 meters of sea level equivalent locked up in the ice in Antarctica alone. So, the 70-meter line brings us right up to this point here with the 70 meters of sea level rise. So, pretty catastrophic for Canterbury, not only for the city of Christchurch. So, and of course, the reason for this, why Antarctica is so important, is that Antarctica has about 85.7% of the world's ice. So that's pretty large. That's large compared to the Arctic, only about 12.8%. We hear a lot about the Arctic, and that's because the Arctic average temperature is very much warmer than the Antarctic. So we tend to hear what's happening more in the Arctic. But the most ice is sitting in Antarctica. And a 1% change, which isn't very much, will result in 70 centimeters of sea level rise. 100% goes to the 70 meters that I've already talked about. So I think we're not asking the right question. So it's not what if Antarctica warms. It's really more about the rate of change and how fast things are going to change in the future. And it's about what's happening now and what's going to happen in 10 years, 100 years. And that's the sort of questions I really want to address this evening. So here's the background. Here's the outline of my talk. A little bit of background around global warming. But then the bigger question, what's happening in Antarctica now? Is climate change affecting Antarctica? If so, what's happening to the ice? How fast is it melting? What's happening to the biota? A little bit of information of that. As a geologist, we can't ignore what's happening in the past. So I just want one example really from the past. What about the future? Have a little go at that. And then what does this all mean for Christchurch? It's easy to be confused about global warming. We get lots of messages. Just on the news, even last night, was global warming's leveling off. It's not happening. A sort of little piece on the 6 o'clock news last night. often signals about Antarctica. You'll see there icebergs may be a sign of global warming. So not surprising if people are confused around what's happening, particularly around Antarctica. Here's another heading from the newspaper: vast ice shelf collapses in Antarctic meltdown. Or else, Antarctica defies global warming. So which is it? What's actually happening? So hopefully, by the end of this evening, and I tend to speak for maybe 3/4 of an hour and then have some time for questions, but we'll sort of see how it goes. So just, again, a little bit of background. This is a temperature curve. We'll be looking at some curves. This is, This is taking us back, so temperature on the left, time, taking us back just 20,000 years. And this was when our Earth was coldest, at the last time it was coldest, when ice was at its maximum. And temperatures have warmed slowly from this cold time up to 4,000 or 5,000 years ago, and then global temperatures have cooled, and this is all to do with the amount of solar radiation reaching our Earth from the sun. But then, in the last, whatever, couple of hundred years or less, temperatures have risen dramatically. So we've bucked the trend from natural variation to a sharp increase. And sea level, because we've melted a fair amount of ice, has risen 120 meters during that time. So imagine standing in Godley Head, looking out to sea, and seeing that sea level 120 meters lower than it is today. And this is, again, a curve that people are familiar with. We're not going to argue about the fact that temperature is rising. Our Earth is warming. That's definitely happening. And this shows a graph from 1860 right up to today. Maybe it has leveled off a little bit, but it's a bumpy ride. It's not a straight line. Our Earth isn't warming uniformly, or change isn't taking place uniformly. And what's all this due to? Why is our Earth warming? Well, it's warming because of increases in greenhouse gases. Again, no argument about that. It's due to what we're doing here, the emissions of greenhouse gases that we're putting up into the atmosphere. But an important point is that if you go back before 1850, carbon dioxide levels in our atmosphere were below 280 parts per million. And they've been like that for a long, long time. Even the last time they were above that was probably back 3 million years ago. And that's a time period I want to look at a little bit later on. And carbon dioxide levels have been rising since the 1850s. And this is a very common diagram here, which shows that we've passed through this 400 parts per million index just this year. So in 1955, we were down here just about 300 parts per million, and here we are, we've smashed through this 400 ppm level just this past year. So it's about a 33% increase in carbon dioxide levels just over the time that I've been around on this Earth. So it's pretty amazing what we're doing to the atmosphere. So the question is, what impact is all this having on Antarctica? Is climate changing in Antarctica? How stable is the ice? What's happening? So, different countries have had stations in Antarctica taking instrumental measurements for the last 40 to 50 years. If you look at most of these records, there's South Pole. This is Halley Station here. There's lots of bumps, but they're basically pretty flat statistically. So most of Antarctica isn't warming. So when you see those headings about defying global warming, then that's actually not too wrong. But there's one part of Antarctica that's warming very dramatically, and that's this Antarctic Peninsula region that I will talk about in detail. And here's the profile, here's the graph, and you'll see that here on this picture as well. So the Antarctic Peninsula is currently warming faster than almost anywhere else on the planet. It's warmed really by about 3.5 degrees over the last 50 or 60 years. And in fact, what's really interesting, winter temperatures are warming faster than summer temperatures, and you'll see the figures there on the bottom for winter temperatures. So Antarctica's changing unevenly. And this sort of shows it really quite nicely because we have here a summary of temperature trends from 1981 to 2004. And really, quite a bit of Antarctica is during this time period is actually cooling. It's certainly not warming very much. And the area in red, the sea, and the Antarctic Peninsula, again, supporting that diagram that I showed you, is warming really very dramatically. So on the one hand, it's right to say Antarctica, people will say, oh, Antarctica isn't warming, so that's sort of right. And other people will tell you Antarctic's really warming, and that's sort of right as well, but you've got to look at it. You've got to tell a little bit more. You've got to give a little bit more information. This is another diagram that tells a similar story. It's actually based on a slightly different data set from 1957 to 2006, so over a longer period. Again, we're seeing this exact same pattern here of intense warming in West Antarctica and the Antarctic Peninsula, and a little bit of warming perhaps over the rest of the East Antarctic ice sheet. So that's the sort of pattern over Antarctica. Now, why is this? So why are we getting this uneven change over Antarctica? And anybody who came to Adrian MacDonald's lecture 2 weeks ago will realize how important the ozone hole is in dominating and being the key influence in both New Zealand, in southern hemisphere climate. So it's the ozone hole that's been dominating the climatic response or the atmospheric response over Antarctica. And I'm not going into the physics behind this, so you can look back at Adrian's lecture from 2 weeks ago where he explained it to anybody that was there. But I'm more interested in the effects of this. So, and of course, humans, we were responsible for this ozone hole. So on the one hand, we've sort of creating the major influence on Antarctica. And what the ozone hole is doing, it's influencing circulation patterns in the southern hemisphere, and particularly over Antarctica. And it's changing the dominant pattern. Well, there's two patterns here for the pressure systems, which we refer to as the Southern Annular Mode, or SAM for short. And we're basically moving from this is 1955 to 2010, when SAM was in this negative phase, which is this pattern here, to a more positive phase. You see the dominance of the red here, to this phase here. And what that's doing, there's just a couple of important things to point out. So you'll see how this is where the westerly winds were located in a negative phase for SAM, that's down here. The westerly winds are reaching New Zealand here. And when we move to this more positive phase, the westerly winds are much closer to the Antarctic. They're much more intense and stronger, and coming across the northern part of the Antarctic Peninsula where we're getting that warming. And we're getting the easterly winds reaching New Zealand outside of that. So we're getting this pressure drop in the center of Antarctica. We're getting the increase in the, make sure I go around the right way, the westerly winds are much stronger around, and they've increased from about 1980. And there's another important low, which you might just see in their low pressure system in here, which is also quite important. So basically, the take-home message is the ozone hole influencing the circulation patterns and affecting the climatic response that we're seeing in Antarctica today. What else is happening? The oceans are warming. And this is a compilation of changes in ocean surface temperatures around Antarctica. And these are centigrades changes per year. So yeah, the Southern Ocean, really cold, but it's dramatically warming, which is also affecting the whole system. So we know the Antarctic Peninsula is warming. We've just seen that. So what's happening? What's the response in the Antarctic Peninsula to that warming? The westerly winds, this is the peninsula here. This is an amazing picture looking really right across Antarctica to the Ross Sea on this side with the Transantarctic Mountains. So the westerly winds, of course, are coming around this way and beating this western side of the Antarctic Peninsula, coming over the mountain range, and you're getting warm winds coming down on this eastern side. So what's the impact on the Antarctic? Well, these ice shelves, and this is not new, but the ice shelves are disintegrating on the Antarctic Peninsula. The ice shelves are floating, so that's ice that's already floated, moved off the continent, down into these oceanic areas where we have thick floating ice. And these ones with yellow stickers on them, they're the ones that have already disintegrated as a result of this warming. This ice, of course, is already floating, so it's not impacting sea level. But there is a very important implication of the collapse of these ice shelves. So 1995, 2002, these were very warm summers, and two of these, the Larsen A and the Larsen B, pretty dramatically collapsed during those very warm summers. So basically, we were getting melting on the surface of these ice shelves, seeping into crevasses, and resulting in the disintegration of these ice shelves. So there we were in 1995, the Larsen A, and 2002, the Larsen B collapsed. So think of these ice shelves as a sort of stopper, as a buttress. So what they do is they stop a lot of the ice on the continent, on the peninsula in this case, from moving rapidly off the continent into the ocean. And as soon as we take that stopper, that buttress away, the ice has speeded up and moved very quickly into the sea. And measurements that have been made by scientists show that the ice is moving approximately 8 to 10 times faster when these ice shelves have been removed. So as I say, the ice shelves themselves don't affect sea level, they're floating, but it's the ice moving off the continent into the ocean that does affect sea level, because it then melts and moves away very, very rapidly. And this just shows those ice shelves again. So they're really a very sensitive indicator of the warming that's taking place on the Antarctic Peninsula. And these ones in red have already disintegrated. There's still large ice shelves shown here that are still there. And if we continue to get warming in the peninsula, we'll undoubtedly see these ice shelves disintegrating into the future. So that's the ice shelves. What about sea ice? And again, we often hear what's happening to sea ice. And the last year, the amount of sea ice around the Antarctic was bigger than it's ever been. So, of course, climate change skeptics have jumped on this and say, hey, look, sea ice is increasing around the Antarctic. What's going on here? And sea ice is really important for a number of reasons. And one, so this is sea ice here. This is sea that's frozen. But it's like a great big mirror. So all the ice on the Antarctic is reflecting that solar radiation back out into space and actually helping to keep our Earth cool, working in the opposite sense to global warming. So if we don't have sea ice, that sort of mirror disappears, and the oceans will warm even faster because they'll be absorbing more of that heat. So yeah, we've had a record maximum for sea ice extent around Antarctica. But it's a little bit more complicated than that. This is sea ice, frozen sea here. The red areas show areas where sea ice has increased, and the blue areas show areas where sea ice has decreased. So it's really a little bit of a shift, a little bit of a change in the pattern, with it increasing in this area here and across here as well. So the sea ice is important because it's that big mirror, but it's also important in terms of productivity in the Southern Ocean. And it's also important when it forms because it actually controls the global circulation pattern. It sort of drives, the formation of sea ice sort of drives the ocean circulation pattern. So it's really important that sea ice sort of continues to form around Antarctica. And this, again, we often hear we often hear about the changes in sea ice in the Arctic and compared to the Antarctic. And this diagram shows how the changes in the comparison between the changes in the Arctic compared to the Antarctic. So the Arctic, we're getting massive decrease in the extent of sea ice forming each winter. I see all these negative figures for all the different areas. And here's a summation for the Antarctic from 1980 through to 2005, showing how it's been increasing. And just last year, as I say, we've had that very dramatic, we've had the biggest extent of sea ice ever recorded. And these figures here, again on the right, show how the maximum increase area has been on this side, on the Ross Sea, and on the peninsula side, we're getting that decrease. And we think this change in the distribution of sea ice, again, is due to the ozone hole and due to changes in the wind pattern and changes in the circulation pattern of the atmosphere. There's a lot of science debate. Again, Adrian did a very good job in explaining that 2 weeks ago, so go onto the YouTube and listen to that if you want to know more about that connection as to why the sea ice is changing. But it seems, again, like the dominant control on what's happening around Antarctica is that ozone hole. And that's driving the circulation pattern and driving the changes, even in the ice patterns. So we've looked at temperature, we've looked at sea ice. What about the ice sitting on the continent? Because that's where all the sea level rise is tied up. That 70 meters is tied up in the ice. So what's happening? Are we losing the ice? So I just want to talk a little bit about the two ice sheets. We've two big ice sheets sitting on Antarctica. We divide the ice sheet, I guess, up into two is more accurate. On the right-hand side, we have the East Antarctic ice sheet, and this is a section along this line across it. So this is really thick, 3 to 4 kilometers in thickness. It's sitting mostly on Antarctic land that's above sea level. If you remember that second diagram that I showed you, there are small parts that are below sea level, but for the most part, it's sitting above sea level. There's 60 meters of sea level rise contained within this ice sheet, so if we lose it, that's serious. But we're really fortunate. One, it's so cold, and two, it's sitting on land that's mostly above sea level. So the temperatures across the top here are way down in the minus 60s, minus 70s at various times during the year. So it is really cold. So we have to warm our globe an awful lot to remove this. So that's pretty good. But we're not so confident about the West Antarctic ice sheet. So this is much more vulnerable to change. And I'll talk about that a bit later as well. So that's what's on the left here, the West Antarctic ice sheet. This is a section through it. It's thick. It's not as thick as the West. There's only 6 or 7 meters of sea level rise contained within the ice here if it melts. So not so bad, but still pretty serious, as we'll see later. But the worrying thing is that most of it is sitting on land, we say grounded on land that is actually below sea level. And again, refer back to that diagram I showed you in the second picture. which showed a large part of West Antarctica is actually below sea level. And if we'd no ice, it would be sea. So the warming oceans can come in underneath the ice shelves, thin the ice shelves, and cause problems with this ice, West Antarctic ice sheets that's sitting on this land that's below sea level. So we are worried, we are concerned about the stability of the West Antarctic ice sheet and how long it's going to last into the future. And we'll come back to that later on. So what scientists want to know, and this is some of the research that we do here at Gateway Antarctica at the University of Canterbury, is look at the mass balance of the Antarctic ice sheets and see, so it's really how much is it snowing, how much is it building up on the center, and how much is it melting or breaking up on the edges. So if the snow melts or is discharged faster than the snow accumulates, sea level will rise. So it's pretty simple. So it's that balance between what comes in and what comes out that we're really interested in. And you may ask, how the heck do we measure this? Well, fortunately, we've got some satellites circling Antarctica. And this first image that you see here is a satellite that measures gravity. It's called GRACE, Gravity Recovery and Climate Experiment. And that basically measures minor changes in gravity, which we relate to changes in the weight of and size of the Antarctic ice sheet. And you can see from this the areas that are thinning and disappearing, and I'll come back to that also. So this is really good. It's probably the most accurate method that we've got. The second method is we try and measure changes in height. So that's related to whether it's snowing more, whether it's disappearing and melting more. So we use radar, again, for measuring the surface elevation of the ice sheet. It's complicated, and there's a couple of reasons there why it is complicated. It's tricky to get an accurate measurement. But these are the sort of things that scientists are working on to try and measure exactly the mass balance or what the changes that are taking place. There's a third method, the budget method, and that's simply trying to calculate, on the one hand, what comes in to what's lost. And that's really the rate of flow that's taking place across this grounding line, or this area where the ice sheet is pinned to the ground below. So this is the budget method, and it's obviously the difference between what's accumulating on the one hand and what's disappearing on the other hand. So these are three different methods. So you can imagine the literature is full of scientists using different methods, getting different results, and that's what we have to try and work out and see, well, what really is happening to these ice sheets. And this is a result that came out in 2005. And this shows that, you'll be pleased to hear, most of East Antarctica is accumulating. It's growing, it's thickening, it's more snow is falling than is disappearing. The blue-black areas, however, look at West Antarctica. That's a little bit worrying. So that's where we're seeing the ice is disappearing from this area here. But of course, what we have to do is try and integrate this across the whole continent. We have to look at the balance across the whole continent to see, does the amount of increase outweigh the amount of decrease here? Is the whole thing growing, or is the whole thing shrinking? And again, that's the sort of research that's going on. So let's have a little closer look at West Antarctica. So this is the West Antarctic ice sheet. Again, we're really lucky. We've got these two big ice shelves here. That's still acting as a buttress. It's stopping most of this ice flowing off this part of West Antarctica, and the same here. But look at this segment here. There's no ice shelf, no big ice shelf on this area. And it's also the site of an area where we've got some warm circumpolar deep water coming up. So if you remember from that other slide I showed you, this is where the blues and blacks were, and that's where we're losing ice. So let's have a little closer look at this area. If all this ice was to melt, sea level would rise by about a meter. There's two very big ice streams or glaciers coming down here, the Pine Island and the Thwaites Glacier, and they're very large, and they're draining the ice out of this area here. So scientists have been busy measuring what's actually happening in this area, and two of these glaciers are actually moving much faster than they were. The Pine Island Glacier that I just pointed out is moving 60% faster than it did in 1970. The Smith Glacier is moving 83% faster than it did in 1992. So this is another area that's warming, and we're seeing this accelerated rate of change in this important area. And it is resulting in sea level rise. It doesn't sound much, but it's 2 millimeters of global sea level rise per decade, per 10 years. And that's about 10% of the global sea level rise in the last 10 years, which is, well, it's rising about 2 millimeters per year for global sea level. So Antarctica is contributing through here about 10% of that rise is coming from this particular part of Antarctica. And this tries to do that, to average this out across the whole continent. And this scale is showing the gain, and down here is showing the loss. And this shows the calculations that scientists have done from 92 up to 2006. And the colors represent different papers. And all these scientists here and here are saying East Antarctica is gaining mass, is increasing in size. All the calculations that have been done on West Antarctica during these time periods that you see here show West Antarctica is losing mass, as we've already seen. And if you average the whole thing out, it does show that the whole of Antarctica is losing mass, and therefore contributing to sea level rise in the present climatic conditions that we've got. So that's serious. Antarctica is contributing to sea level rise, quite small at the moment, and the question really is, how is that going to happen in the future? So this just summarizes it. East Antarctica is thickening. We're getting snowfall. Antarctic Peninsula is melting for atmospheric reasons due to the ozone hole. We're getting melting and thinning here on this part, and we're getting a bit of long-term thinning over that part. Unfortunately, we've got those ice shelves buttressing West Antarctica and keeping that ice pretty much in place. Just a little diversion now. I just want to mention something. A really interesting area of research is these dry valley areas. And I'm just pointing this out really because it's showing, in some senses, how stable things have been, even over a long period of time. Because, so these valleys have remained dry. And these are some pictures of these valleys. And parts of these valleys have actually not had ice in them or not had substantial change for 14 million years. So again, we're lucky. Antarctica's been so cold, and some of these areas haven't changed too much. However, the one thing that is changing is the amount of melt. And this is melt that's accumulating and flowing down through the valleys, through these rivers, and these rivers flowing into some of the lakes within these dry valleys. And this shows there's about 12 meters of change in height level of these lakes from 1960 through to the present day. So we're getting more melt. It's accumulating in these lakes within these valleys. But these valleys have been unaffected pretty much for a very long period of time, which is pretty good. We can't have talks about Antarctica without talking about the iconic penguins. And so here they are. So what's happening to the penguins now, and what's going to happen in the future? So, or what's happening to the biota, really? There's 2 flowering plants in Antarctica. And yes, on the peninsula, we know the peninsula is warming. the flowering plants are extending their range across the Antarctic Peninsula. So we're getting more vegetation like what you see here, where the Antarctic Peninsula is warming, which we know about. Scientists have also been doing experiments artificially warming the ground in Antarctica, putting these cloches in place to see what effect they might have. And lo and behold, what you get. These are slightly artificial experiments, but you do find there's lots of propagules and seeds in the Antarctic soils that do vegetate if you change the climatic conditions. So there's lots of issues there in terms of a warming Antarctica. There's another issue about warming Antarctica as well, and that is invasive species are coming in, or there's a risk of invasive species coming in from either through scientists or other visitors to the Antarctic, and also through wind systems. And this is a plant, this is a native from South America that's become established or is at least present on Deception Island just off the northern tip of the Antarctic Peninsula. This may have come in via wind, but it's established. And this is a king crab, Atlantic spider crab that was found also on the Antarctic Peninsula in 2004. So again, this is a risk of warming the peninsula, warming or changing the climatic conditions in Antarctica, that we will see invasive species coming in. So what about the penguins? Well, this is a graph again, Antarctic Peninsula. That's where the changes are taking place. This is an Adelie penguin on the left, and this is a graph of Adelie penguins from this island here. And rapid reduction from 75 to 2005. Offset, I guess, by an increase in the size of the population of these penguins here. So the Adelie penguins are moving south, and they're being replaced by the Gentoo penguins. But overall, we are seeing a shrinking in the Gentoo and Adelie penguin populations on the Antarctic Peninsula. So these iconic species are again being affected by the warming that we're seeing on the peninsula, which is pretty serious. And this is again probably due to the loss of sea ice affecting the primary production. Remember, the sea ice is reduced in extent off the Antarctic Peninsula. Also seeing lower breeding success of emperor penguins in different parts of Antarctica also. So we are starting to see the effect on the biota. This graph from South Georgia, a little bit more sub-Antarctic, but this shows krill decreasing from, this is a crustacean in the Southern Ocean that forms an important part of the food chain in the Southern Ocean. And here's some pictures of a macaroni penguin colony, different type of penguin, 1976. You can hopefully see the density of penguins and far fewer penguins here in the year 2000. I have to say how complicated the whole Southern Ocean system is. So don't forget, and you can easily draw the wrong conclusion even from these graphs that I've shown you and jump up and down and say it's climate change. So it may not be. It's a complicated system. Humans took 300,000 blue whales out of the Southern Ocean, 30 million tons of biomass. So we've really changed the whole balance of the ecosystem of the food chain within the Southern Ocean, and maybe moved from one dominated by whales to one dominated by these fur seals. So we changed the balance, so we're not quite sure exactly what we're seeing happening now. Okay, I want to look back a little bit to the past. As I say, us geologists, we always like to see if we can learn something from looking back in the past. And New Zealand scientists have led the way in drilling a drilling program looking back at how climate has changed going back millions of years, and seeing what we can learn from that by drilling some deep holes in this area off Ross Island that you see here. So some very interesting results which show us how the ice has advanced and retreated with climate oscillations over thousands of years and going back sort of millions of years. And during the cold periods, the ice at the West Antarctic ice sheet advanced over where the drill rig was. This is the way it is today. We sat the drill rig on the ice shelf and drilled down into the rocks. But this is what's really interesting. We found these areas where there was no indication of ice at all. It was simply diatom-rich muds. Now, diatoms are phytoplankton. They have silicon shells, so therefore they form good fossils, and they live in warmer waters. So it's telling us, or the species that we found actually in these were typical of more warmer waters. So this is what we think it looked like for the first time just 3 million years ago. No ice, warmer waters, diatom-rich muds forming on the ocean floor. So I want to just focus briefly on this period 3 million years ago. And this is a horrible diagram, but this is today, and this is going back millions of years. And I want to just focus on this area here. So we can't measure carbon dioxide back many millions of years ago, but we can use some proxies for what we think carbon dioxide levels might have been. And this shows us that 3 million years ago, when we had those diatoms, the proxy record, these red dots and blue dots in here, suggest, and I'll use the word suggest, that the parts per million, that the carbon dioxide levels in the atmosphere were about 400 parts per million back in this time period in the Pliocene. And you can guess what's coming. At that stage, we think the West Antarctic ice sheet didn't exist, and with no evidence of ice from that drill record. We had those muds. The ice had disappeared in this particular site, and the proxy record tells us from looking at these isotopic records that the carbon dioxide levels were about 400 parts per million. And what have we got today? We have 400 parts per million. And it looks like Antarctica was about 2 degrees warmer at that stage in 3 million years ago than it is today. So we haven't warmed to that extent yet. But that the West Antarctic ice sheet may not have existed during these conditions that we see here. And this is how we think it looks. Here we are today with the West Antarctic ice sheet shown in this nice green color here. And here this is what we think it looked like 3 million years ago. When the oceans were warmer, we had 400 parts per million carbon dioxide without a West Antarctic ice sheet. And that sea level would have been about roughly 20 meters or so higher than it is today, with 7 meters of that coming from Antarctica, probably the West Antarctic ice sheet, and of course some of that coming from Greenland also. Okay, getting to the tricky bit. It's easy to tell you what's happening, what's there, and what's... We've got all these measurements through times when people have been visiting Antarctica, but it becomes more speculative when we talk about the future. So you've got the message that what's happening in Antarctica today is dominated by the ozone hole. Now, hopefully, the modelers tell us the ozone hole is going to disappear in 40 to 50 years from now. So we might expect to see some changes in the circulation pattern and changes in the temperature pattern from when that happens. Now, this diagram, which Adrian lent me, shows the size of the ozone hole over various time periods. The gray is the maximum size, reaching this line here. The white is the average. These are various years, recent years, showing the size of the ozone hole. And here we are. This is where we are today, 2013. So it's looking like it's not going to be as big as some of these more recent years. And hopefully we're seeing it getting smaller. So we're expecting the ozone hole to disappear 40, 50 or so years from now, which of course is going to bring some changes. And this goes back to the SAM diagram. You remember the ozone hole is driving us towards positive SAM and those strong westerly winds. So with the ozone hole decreasing, we're going to drive back towards a negative SAM, if you remember that diagram. But don't forget the greenhouse gases are going to increase at the same time, and the increase in greenhouse gases that we're already seeing, the carbon dioxide, is going to continue to drive us towards that sort of positive SAM. And of course, the greenhouse gases will result in a much warmer world, and the physics again behind that is sort of well known. So the effect of the ozone hole will slacken off, but the effect of the greenhouse gases, the increase in greenhouse gases, will become the sort of very, very dominant thing into the future. So what's that going to mean for melting? And this comes back to those lakes in the dry valleys. This is a diagram that shows the amount of inflow, the amount of melting that we get, and the amount of how much water flows down this river, the Onyx River in the dry valleys for the present time. This is what's projected for when the ozone hole remains intact, and this is the amount of flood events and the increase in flow, of the Onyx River into Lake Vanda when the ozone hole completely recovers. So we're expecting to see huge increase in flow in these dry valleys, and we'll expect to see Lake Vanda particularly, or the lakes in the dry valleys, will increase much more and start to fill up these valleys with water, I guess. And this has happened in the past. As you'll see, the lake levels have been up to 480 meters in the past. So it has happened a long time ago also. I'm going to just skip these two diagrams, but it's basically some modeling that we've been doing. One of my colleagues who's here has been doing. And this is showing us, this is projecting into the future, 20, 30 years from now, well, really 2010 to 24, using the IPCC models and showing us where we're going to get changes in precipitation. And this is the changes that we might expect. And of course, it's all around the edge. So we're going to see the changes around the edge. But we're going to run these models through for the next 100 years to see how temperature is going to change, how precipitation is going to change, and how climate's going to change into the future. What will happen to species? Yeah, some species might go extinct, but pretty unlikely in the next 100 years. Ocean acidification is quite serious. Haven't talked about this, but the oceans will absorb more carbon dioxide and become more acidic. And as that happens, some of the organisms that form calcium carbonate shells will stop being able to form their shells and build skeletons as the oceans become more acidic by absorbing more carbon dioxide from the atmosphere. Some of our animals may move, but that's pretty difficult. They'll try to move to sort of colder waters, but they can't because the Antarctic continent's in the way, so they can't really get any colder. In the Arctic, they can move further north to colder water. And of course, some might evolve to, as the oceans warm, to warmer temperatures. One of my colleagues at the university, Bill Davison, he's been doing some experiments on fish to see how well fish can adapt and live in warmer waters and how their metabolism changes. And he found that some of the fish species, this one up the top here, looks like could successfully adapt to living in a warmer water. In fact, was more active in warmer water. But this one here struggled completely in warmer water. And it's like that would be some of the species that might go extinct into the future. Okay, what about sea level? We're getting close to looking at Christchurch now. The International Panel for Climate Change, International Government Panel for Climate Change, the last time their report came out, they suggested sea level was going to rise 18 to 59 centimeters by 2100. Now, this lecture is a little bit premature because the next IPCC report is likely to be out tomorrow or next week, so it's really imminent. But what we think you're going to see is that the projections are going to change to somewhere around about a meter. And that's because the last IPCC report did not include some of the dynamic changes that we're seeing in Antarctica. But they will be included in the next report that's coming out within a week or so. And as I say, it's likely to be somewhere up in this range here. And this is what a scientist from Germany published in 2007 saying, these are really underestimates. This is more like what we're seeing. And this is the same author looking further to 2300 and saying, look, we're heading for 3 or 4 meters of sea level rise by 200 to 300 years from now. And again, some people are saying these are sort of conservative estimates, but this is what we're seeing. So this is our favorite place. This is where we're living, and this is today, where the sea is today. So what is 1 meter going to look like? So this is one meter of sea level rise. And of course, 1 meter is what's anticipated fairly conservative, well, perhaps in the next IPCC report, which is what might happen by 2100, by the end of this century. So, of course, it doesn't look too bad. It's the areas around the Heathcote River, around Ferrymead. These are the sort of red areas here, around the Avon River around here. And of course, some of these areas are red zone, but the red zoning doesn't relate to sea level rise. The red zoning relates more to liquefaction and the sort of substrate and so on that we have in Christchurch. But this is sea level rise, and these are the projections. Also bear in mind that it's not just the sort of sea level rise, it's all the storms that build on that higher sea level. And this is what happened in Wellington earlier in the year from a big storm, and houses that had been there for whatever length of time suddenly were washed away. So if you add another meter of sea level rise, and this is another meter in Wellington, this is what will happen in Wellington. And we had already had those houses been washed away just simply from storms, and we're also, of course, anticipating more storms. So this is back to Christchurch. This is 2 meters. So you can pick out where you live and see how we are. I live just about here, so not so good. So that's 2 meters. That's 3 meters. So you can see the sort of, this is Linwood Ave coming up here, the area to the south of Linwood Ave and around the Heathcote Valley up around Avonside and of course New Brighton. So this might be 200 or 300 years from now. So I mean, with regard to the rebuild of Christchurch, it just depends what's the future. What are we building for? Are we building for a city that will last 100 years, or are we going to build for something that might last 500 years? If we're talking of 500 years, this is undoubtedly 500 years from now. This is where sea level will be. By most estimates. And that's just 3 meters. That's 4 meters. So we're approaching Cathedral Square here, certainly on the next one. That's 5 meters. 6 meters. And then I'm going to jump to 12 meters. And you'll see the University of Canterbury. We're not by the seaside, we're already in the sea. At 12 meters of sea level rise. And this is really where that issue about the West Antarctic ice sheet comes in, and the issues around 400 ppm carbon dioxide and the results of that drilling program. So without the collapse of the West Antarctic ice sheet, we wouldn't expect, I meant to go backwards, I beg your pardon. So we'd expect to be sort of background here in 200 or 300 years' time. But if that comparison about looking back and seeing what happened at 400 ppm 3 million years ago, that's where the 6 or 7 meters from the West Antarctic ice sheet kick in if the West Antarctic ice sheet collapses. And added to that, of course, with the collapse of Greenland, which is already happening. Very briefly, I'll just want to say that this shows from the last IPCC report that we're already on track. We can't stop what's happening at the moment. And this diagram shows 100 years, 1,000 years. This is carbon dioxide emissions. And if we, in the next 50 years or next 30 years, if we manage to reduce our emissions dramatically, that's what will happen. This is the emissions dropping off dramatically if we put some really big changes in place. But the carbon dioxide levels themselves will stabilize after 200 or 300 years, so they'll continue to rise in the atmosphere and then stabilize. Temperature will continue to rise even after we reduce the emissions and then stabilize a few centuries from now. But look at these. These are the worrying ones. This dark one is the sea level rise due just to water expanding due to thermal expansion of the ocean. And this is sea level rise due to ice melting. So these two will continue on up to 1,000 years. So we're already on track for those sorts of changes. Okay, we're at the conclusions. So, oops, I think I must have gone there. So, the last 30 years, the ozone hole has shielded the bulk of Antarctica from the effects of global warming. So we've seen that. It's doing us a favor for the moment. Antarctica is the sleeping giant. There's all that ice, all that water contained within the ice, and thanks to, we're lucky Antarctica is so cold. We're lucky the ozone hole has stopped the warming to a certain extent so far. And Uncle Sam has been influenced by the southern annular mode by the ozone hole, and that's, again, it's warming the peninsula. There's not too much ice there, but it's keeping the rest of Antarctica pretty cold. Parts of Antarctica are losing ice. We saw that in that area of West Antarctica. Sea ice has increased around the Antarctica the past 30 years, most likely due to the ozone hole. The Southern Ocean is warming. We've seen that. The ecosystem will change. The marine ecosystem's already been affected. We saw how krill and penguin numbers have changed dramatically, probably due to changes in sea ice. So when the ozone hole heals, 40 to 50 years from now, we will expect to see the effect of greenhouse gases kicking in and Antarctica warming much more dramatically. Maybe a doubling of carbon dioxide levels unless we do something about it in the next 100 years. And Antarctica is expected to warm by about 3 degrees. West Antarctica, that's the unstable ice sheet, could make a major contribution to sea level rise over the next century. Not necessarily completely disintegrate. But anyway, it seems like we can expect a meter of sea level rise by 2100. Only 15 to 20% of that will come from Antarctica. And this is the more speculative stuff. It's about how sensitive the West Antarctic ice sheet is to Southern Ocean warming, and if our carbon dioxide levels remain above 400 ppm, we could be committed to losing the West Antarctic ice sheet and 7 meters of sea level rise. And the last time that happened, as we know, was 3 million years ago, when sea level was at least 10, 15 meters higher than it is today. And this is that last point. The Earth's response to present and projected global warming has started our climate on a path which we haven't seen for 3 million years and is sort of unstoppable at the moment unless we do something pretty serious about it. So when I started my Antarctic research, nobody really worried what you were doing in Antarctica. Now, Antarctica is a really critical and important part of the global system. And we really have a responsibility. And here we are in the Gateway City. It's a key issue for Christchurch. So Antarctic research really is very, very important for this city. So thank you very much for listening. I want to just acknowledge quite a few people who are in the audience. Their names are there. I borrowed their slides. I've borrowed their ideas. I'm responsible for what I've said about them, but thanks to all those people who've given me material and lent me stuff. A couple of cartoons you might find amusing. There's another one coming up, and I'll leave it there.